Malayaja, what have you given us in the chat window?
Yeah, it would be great if everyone can go to this link and download the Jupyter Notebook files and other files from this folder. And if people have already downloaded Anaconda on their systems, then they can open that up. Or alternatively, people can just open these Jupyter Notebooks on Google Colab. If anybody is unable to do so, please let me know and I'll try to figure it out.
While they do that, maybe you could just outline what you're going to do.
Okay. So first of all, thanks, ma'am, and thank you to the other organizers for giving me the opportunity. Yeah, Professor Sunetra, Professor San, and Professor Arun to give me the opportunity to be part of this workshop. And the purpose of this tutorial is to help students and young researchers get started with network-related computations and simulations using Python and the NetworkX package. And I realize that there are other network calculation packages like GraphTool and iGraph, but I found NetworkX to be reasonably simple to start with. So here goes. So you will probably see all of these files in the shared folder. And it would be great if you could make a copy of all of this on your system or on your Google Drive. So maybe I'll wait around for 1 or 2 minutes for people to do that. So does everybody have access to the Jupyter Notebook? Okay.
Zubair Malik, she's already shared the file on Google Drive, I think. Malayaja, there's a question in the
Yes, ma'am. I shared it again. Perhaps Zubair joined us after I had put the link in the chat.
Yeah.
Okay. So to start off, for people who haven't used Python and or Jupyter Notebook, a quick intro to that is that Jupyter Notebooks are an easy way to try out code before putting all of it into script files, and you can share and collaborate easily using Google Colab, like we share and collaborate documents on Google Docs. And also, if you've downloaded Julia and R kernel, a Jupyter Notebook can run Julia, Python, as well as R. So that's why it's pretty great. And So as the NetworkX website tells us, NetworkX is a Python package for creation, manipulation, and study of networks. And I'm going to start off with importing the NetworkX library as well as other relevant libraries. And I want to see what NetworkX version I have. So that's what I'm going to run in my second cell. And I hope everyone has access to the notebooks by now, right? Can you guys tell me in the chat? Okay. Okay, great. Okay, so I seem to have the 2.4 version of NetworkX, but I believe the latest stable version of NetworkX is 2.6 or so. So you can perhaps, I perhaps need to update my package anyway. So this is a link to the website as we saw. This is the second link is to the documentation. And the documentation also comes with nice tutorials, and you can perhaps go there after this tutorial. And so a network is basically consists of a set of vertices or nodes connected by links or edges. So in order to define a network, we need a set of vertices and a set of edges. So let's start by defining a graph using the NetworkX graph function. And let's see what type of object this is. And it comes under the graph class. And so let me add a node to this graph, and I can do that using this cell. And I can see what my network looks like so far. And so far, it's a lonely node sitting in front of you. So let me add 2 more nodes. And I can do that by defining a list of nodes. I'm going to call them 2 and 3. And I'm going to use add nodes from function. And now my network looks like this. And I can also add nodes where the node has a certain property. So here, the property that I'm giving to my nodes is mask. You can also give a property called colors, based on which you can color your nodes differently when you're plotting. And let me look at the node list using this function. And I get 1, 2, 3, 4, and 5. And I also want to see what the individual property of the individual nodes are. So I'm going to then put in 1 here, but node 1 doesn't have any attribute, whereas node 5 does. Great. Okay, now I'm going to add edges. In order to do that, I'm going to first create a list of tuples where each tuple has the source node and the target node of an edge. And then I'm going to use the add edges from function. And now my network looks something like this. As with nodes, I can give attributes to edges, and I can do that by adding a third element to the tuple of my edge list. Here, this is just the weight of the edge. So now my network drawing just has more edges. And if I want to if I have a network and I want to see what the edges are and what the edge attributes are, I can do so using these functions. So as you can see, this edge 1, 2 has no attributes because we gave it none. Okay. How is the weight of the edge represented visually? Okay, so visually you can, so Hari asked this question. Visually, you can make the edge thicker. You can also maybe give a color gradient. Say blue is for weight 0, red is for weight 1, and so on. So I guess that's how you can do that visually. Is that okay, Hari? Okay. And so suppose you have a network and you want to see what its adjacency matrix is. There are many ways of getting the adjacency matrix, and this is one of them, where you put in the adjacency matrix into a NumPy matrix, and this is what it is for our particular network, which has weighted edges. So oftentimes we have to store network data into files for using later on, and storing adjacency matrices can be very expensive in terms of the amount of data that it takes, given really large networks. So a better way to store data is by using something called an edge list. And you can look at the documentation in the link given. This is basically a list of all the edges in the network. And you can also put in whatever attributes these edges have. For example, weight is 7, color is green, and so on. So here, 1 is the source node and 2 is the target node and the edges between them. Great. And you can read an edge list using this function and write an edge list of a network that you've made using this. And an important thing to keep in mind is that the edge list has to have a particular extension. Okay. One thing that is slightly bad about using edge lists is that suppose you have a node in your network that isn't connected to any other node. So that won't get represented in your edge list. So a better way to not be data expensive and still get all the information off the network is to use something called an adjacency list. And the documentation is here. So this is basically the source node, and the target nodes are B and C. And you also have, so you have basically a node A, which is connected to node B, and A is also connected to node C. And I hope everybody can see what I'm drawing. D is connected to E, and you have F hanging about on its own here. And again, you can look at the documentation for figuring out how to use it. Reading and writing adjacency lists is similar to how we do it for edge lists. Okay, and another interesting part about network graph is that you can have mixed form of nodes. Nodes can be any object, a number, a text string, or an image, or another graph. So to give an example, I'm going to define another graph G1. and I'm going to define this edge list where I have nodes 0 to 6, and the 7th node is called spam. Okay, so what is spam? Basically, for people new to Python, there is a comedy TV show called Monty Python, which was the inspiration behind the name of Python. So a lot of the examples online, and there is some running joke about spam in that TV show. So a lot of the examples of Python online will have that. I haven't seen the show myself, so I don't fully understand the joke. But yeah. So I'm going to draw this weird network using a circular layout. So networks can be given a particular layout. You can either define them yourself, or you can use network X defined layout. Here I'm using circular layout. Suppose I want to use something called the Kamada Kawaii layout, which does some sort of optimization with path length. And then a random layout is just giving each node a random position. So it's all over the place. And a circular layout is basically all the nodes are in a circle. Okay. So I guess I've just covered very basic stuff so far, but any questions?
Malayaja, my class is supposed to be here, and the next part, namely the shortest path length, is what they are mostly puzzled about. So spend a little bit of extra time on that.
Okay. 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 So I'll get to that in a little while. Any way to fix position? Yes. So Hari asked, is there any way to fix the position of the nodes ourselves? There is, and I'm getting to that in a minute. Okay, so I'm going to use this code snippet to list all the nodes. And here I have 0 to 6, which are numbers, and spam, which is a weird name of a node. And I'm going to list out the edges. And as you can see, there are 2 parts of this network that aren't connected to each other. And this connected component lists what these 2 parts are. Okay, and as Man said, let's get to average shortest path length of G1. And oops, we have an error because there's like, can anybody tell me why? Yeah, that's right. The graph is disconnected. Also, here your error is right there in front of you. But suppose you have issues with functions in Python or any related package, what you can do is you can write the name of the function and you can write a question mark and press Shift Enter, and the documentation will pop up.
Oh, so it's a built-in function, is it? Shortest path?
It's a built-in function in Network X, yes.
Okay. So if in Jupyter, at least it's a built-in function, or
no,
will it be not?
It's a built-in function whenever you use Network X. Whenever you import the Network X library, it will be available for you.
I see. Okay, that makes life easy, guys.
Yes. Yes. And so, like I said, if you want to look at the documentation of any given function, you can use one question mark. If you want to look at the documentation as well as under the hood of the function, which means if you want to see what exactly the code is behind that particular function, you type 2 question marks and press Control Enter and you'll get everything. So this is one of the good parts about using a Jupyter notebook, that you can pull out documentation very easily. Okay, so now to average clustering coefficient. As you know, this is it measures how well connected a network is, or in other words, how many of your friends are friends of each other. And you don't need to have the network to be connected to define clustering coefficient. So that's what we have. Now suppose I add an edge between nodes 2 and 6, which is this fellow and this fellow. And now my network will be connected, and I will be able to get a finite average shortest path length. And obviously my clustering will change. Lastly, before moving on, there is also a function to tell you the shortest path between any 2 nodes in your network. So between node 1 and node span, this is the shortest path. Okay. So Bala Rajesh asked, so basically you constructed the graph from each individual edges instead of defining the edges at a time using some tricky algorithm. Yeah. Yeah, so because I'm using a small network to show certain things about network X, I can do that. But suppose, depending on what your use case is, suppose your use case requires you to have a tricky algorithm, as you say, to grow a network, then that is what you have to do. Okay, so next, let's look at a degree distribution. So we're all cool up until now. Okay, so a degree distribution, as you might know, is basically gives you some sort of a probability of a randomly selected node in the network to have a certain degree. So let's look at the degree distribution of this funky graph here. So there's a question which says, can we convert a matrix into a network? Yes, you can. So you can have an adjacency matrix. I think that's what you mean. And you can input it into your network instead of, giving it an edge list or whatever. Okay. Okay. So I'm just looking at the funky network that we have, and I want to plot the degree distribution. So let me first look at the degrees of my the nodes in my network. So this function basically says that node 0 has 3 edges, or it has degree 3. Node 2 has degree 4, and node spam has degree 2, and so on. And I can use this code snippet to just output the values from the degree values from this. And I can sort this in a descending manner. This is the output. And I use the function counter from this package called collections. to get something called a degree count, right? Which basically means there are 3 nodes which have degree 4, 2 nodes which have degree 3, and so on. And I can sort of uncouple these keys and values. And then I can define I can normalize the count to get the degree. Then I can plot it like this. So I'm giving a detailed sort of example of how to calculate degree distribution, because as far as I know, there is no inbuilt function in network X to do so. Okay. And before I close this notebook, we use the graph function so far, which is basically a simple undirected network. By simple, I mean that it doesn't have, it has only one direction in the edges. There are also digraphs and multigraphs where you can have directed edges or parallel edges that are defined in the network X package. And you can define objects, graph objects like this. Okay. So if there are any questions, you can ask them before I move on to the next part of the tutorial. What do you mean by parallel edges? So sometimes you can have, so first of all, you can have parallel edges when you have a directed graph where an edge from 1 to 2 is not the same as an edge from 2 to 1. But in a undirected graph, you can also have parallel edges based on, say, you have an edge based on time. So at one point of time, you create certain edges in your network, and at another point of time, you have certain other edges in your network. But then if you look at your network, removing the timestamps, you can see that there are parallel edges. So all of these things will become clearer once you have concrete examples and once you look at papers, etc. Okay, great. So we can go to the next tutorial. Okay. So Sayantan asks, can we draw multi-layer or multiplex networks using these syntaxes? So I think in order to do that, remember how we said that we could input the position of individual nodes either using an inbuilt layout or user-defined layout. So I guess you'll have to be a little clever in giving proper positioning to your nodes in your visualization. But in terms of working with the network, you can. work with.
If I may interrupt.
Yes, ma'am.
A very old-fashioned way of doing it is to simply number the nodes serially. Okay, so that's something which you can do for a network which is almost in any dimension. I don't know if it's convenient in terms of applications, but for 2D networks, at least I often do it.
Okay.
So, okay, back to you, Malayaja.
Okay. So there's another question that says, how do we input the direction of edge for a directed network? So to do that, let me go back to this, the previous tutorial. So if I have an edge list that looks like this. So if I've defined G0 to be a graph, it won't matter whether I write 1, 2 or 2, 1. But if I've defined G0 to be a digraph, then 1, 2 would mean that 1 is the source node and 2 is the target node. And that's how direction would be defined. Is that clear, Kadambari? Okay. And to also answer a previous question about weighted networks and how to draw them, I think there was a question earlier. You can use something called edge colors, or so you can put input here into your drawing of the network to give different edges, different widths and colors based on what you have defined. So widths and edge colors and all of that can be put in here. Okay. So going on to the next tutorial, here we'll be looking at different graph generators. I guess you have learned about random graphs and the Voxogas small world graph model and the Barabasi-Albert graph model. So we'll be looking at that towards the end of this tutorial. But to begin with, let's look at something simpler, which is a complete graph, which is basically every node in this graph is connected to every other node. This is what we have here. And to give you an example of what the position looks like here in this circular layout, what we've put in here is basically a dictionary of the nodes with its X and Y coordinates in terms of position. And suppose I don't like this position and I want to input my own position. So I've made this new dictionary. So I'm going to put that in as my position. And so now my network looks like this. I've also changed the node color here to be red. What is slightly bad about this positioning is that I can't clearly see the edge between 0 and 4 and the edge between 3 and 1. So I'm going to change this positioning a little. And now this is better. So I guess what I'm trying to say is that you need to be careful about these things while visualization. Okay, and with the same network with a random positioning result. And another network which is made up of just a line or a path. An example of that is here. This is a path graph made up of 5 nodes. Then you might have come across something called bipartite graph, in which your set of nodes is broken up into 2 sets of nodes, such that links can only be created between 2 nodes from different sets. This is a complete bipartite graph where one set of nodes has 2 nodes and the second set has 5 nodes. Okay, now let's come to Erdős-Renyi random graph. Ma'am, have the students studied this in class?
Well, they have heard of it. Yeah. See, they've heard of small world, they've heard of scale free, and they've heard of random graphs. So they know what each one is. Small world and scale free, we did in detail, but that's only our students, my complex networks course. There are many students here. So
that's right. Yeah. That's right.
So you should spend 2 minutes at least explaining.
Yeah. So this model was developed to study real world networks when it was assumed that where the assumption was that connection between 2 nodes has some probability of existing or not existing. To see a detailed documentation of at least this function in the NetworkX library, you can have a look at it here. Okay. And so basically, in the Erdős-Renyi random graph, you start with, say, n nodes, and you start connecting pairs of nodes with a given probability p, small p. And this creates a graph with, on average, p times n minus 1 divided by 2 edges. And in the large n limit, the degree distribution that you get is a Poisson distribution. And we'll see all of that here. So I'm going to make a network with 1,000 nodes, and the probability that 2 nodes are connecting is 0.0015. And although I've written a code snippet to draw the network, it doesn't make too much sense to draw it because it will be a mess to view. Okay, and I've written a bit of code snippet to look at the degree distribution, which is what we see here. And I've also plotted a sort of Poisson distribution that ideally should be followed. Now, suppose, but the Poisson distribution comes closer to the degree distribution for the large n limit. So let's look at a larger network made up of 10,000 nodes. And let's look at its degree distribution. Okay. So we see that it looks pretty good now for a larger network. Okay, next, we'll look at the small world network model proposed by Watts and Strogat. You can have a look at the documentation here. So basically, the idea, I think Professor Sayan also mentioned this at the beginning, is Watts and Strogat came up with a way to construct a network between random networks and regular networks, which is what they found real world networks to be like. So real-world networks they found had high clustering coefficients and small characteristic path lengths, which is why they said this is somewhere between regular and random networks. So the algorithm to make such a network is to first start, the algorithm that at least Watson Progress came up with was to start with a ring lattice with n nodes, such that each node has a degree k, or it is connected to k other nodes. And then you rewire each edge randomly with given probability small p, and you make sure that there are no self-collections and there are no duplicate edges, meaning there are no parallel edges. So you can write your own code for that. That's a good exercise, but NetworkX gives you sort of an inbuilt function to create a small world network. So let's look at what it, so for 1,000 nodes, where each node to begin with has 4 edges, and the probability of rewiring of each edge is 0.2. This is what I get. It doesn't look like anything, but it is what it is. And I have used, in this drawing, I have used the circular layout to position the nodes, which is where all the nodes are at the edge. And now I use this other layout. Again, it won't, it'll be a hairball. So perhaps you can look at other tools like Gephi to visualize such large networks. Okay, so there's a question that says how to plot networks with higher order node dynamics. That's a good question. Okay, wait. I'm a little confused. Can you explain what you mean by higher order node dynamics? I'm confused because I do work in higher order interactions. So I want to make sure what you mean.
Yeah, Kolhapur Singha, Malaysia needs a clarification. Maybe you can continue, Malaysia, and when we get a response, you can.
Yeah, I'll do that. Okay. So, so we're coming back to this hairball of a small world network and plotting the degree distribution. And we can, what is interesting, as you all probably know, is that it peaks around 4, which is what our original degree was for all the names. Will obviously happen. And let's look at a network, a small world network that is much larger. Let's see if my very old laptop can take this. I'm not going to plot this because it takes 3 to 5 minutes to plot, but I did this beforehand and the visualization looks like this. So don't do this kind of visualization on NetworkX. Maybe use something like Gephi to visualize such large work. Okay, and again, the degree distribution looks like this. And again, it peaked at 4 as expected. Okay, so let's come to scale-free the scale-free model, which is a model for growing networks. So far, the random graph, the small world network was sort of a static network, but this is a model to grow network, and you can look at the documentation like this. And here the idea is that most real-world networks that grow by adding nodes, and the likelihood of a node attaching to an already existing node will depend on the degree of the existing node. And the resulting degree distribution has a power law, and a lot of real-world networks seem to have this kind of degree distribution. But you should be aware that in the community of network scientists, there is active and lively debate about what to call a power law degree distribution and what is not. So you can get into that in detail later. Okay, so the question that we were discussing earlier, each node itself can be represented as another node. How to plot networks with higher order node dynamics. The clarification is each node itself can be represented as another network, like Kronecker product networks, or we call them network of networks. Okay, I'm still a little confused. Can we perhaps discuss this after the tutorial? Okay.
You could send us mail for forwarding to Malayaja, okay? So that, yeah, she can answer your question.
Great. Yeah, so to quickly summarize how Baravasi-Albert model, what the Baravasi-Albert model is, first they start with a small number of nodes. And at each time step, you add a new node with a given number of edges connected to existing nodes. And as you add, with each time step, as you add more and more nodes, like I said, the probability of edges between the new node and the existing node will be dependent on the existing degree. And let's look at one such network with which will have 1,000 nodes, and at each new node will connect to 4 existing nodes.
Malayaja, I thought, see, the at 5:30 we actually have a break. How far do you think? How much more time do you think you need?
I think 5-10 minutes. I'll run through.
Okay, so you have 10 minutes.
Yeah.
Yeah.
Yeah. So again, we see a hairball. Let's look at the degree distribution, and let's look at a log-log plot of the degree distribution, and I guess you can figure out the Fowler behavior from this. For a bigger network made out of 10,000 nodes, and again, each incoming node is going to be connected to 4 existing nodes. The network will look something like this, but I'm not drawing this because it will take 3 to 5 minutes on my system. And the degree distribution looks more like a power law for this network. Okay. Excuse me. So before I go on to the next part, very quickly, does anybody have any questions so far?
Somebody wants to know if the recording will be shared with us. Sunitra?
Yeah, it will be put up in the website.
So you can go to the last tutorial now, and I'll quickly run through this. So if you look at the documentation that I have linked to, you can see that there are different kinds of algorithm functions based on coloring, clustering, and finding communities. And all of these things are available within Network S. What I'm interested in is finding cliques, because this is related to the work I do with Professor Neelima. And very quickly, a clique is basically a complete subgraph. So this single node is called a one clique because it's made up of one node. This two nodes that is connected by an edge is called a two clique. This filled triangle is called a three clique. And this filled tetrahedron is called a four clique. And notice that this triangle has three two cliques, which basically means it is made up of this two clique, this two clique, and this two clique. And similarly, this tetrahedron, is made up of four triangular faces and a certain number of edges and a certain number of one clique. Excuse me 1 minute.
Are you there, Malayaja? There are two questions in the chat window.
Yeah, I had gone to get a sip of water. Yeah, so one person says, have you modeled any real world data with scale-free distribution? Has it matched? Yeah, so from what I understand, this is an interesting question. You can look at this review paper by Aaron Closet, where they do this. And they have a very sort of detailed calculation about how to calculate the power law, the power law in the power law distribution. So perhaps you can look at that. And the second question is, how can we draw a scale-free network with a fixed gamma? Okay, from the top of my head, I don't know if there is a function in Network S to do that, but there are algorithms with which you can do that, but I'm drawing a blank currently. As in, I can't pick it out right now and tell you. I'll have to look it up and give you an answer to that. So another question is, can you work with dynamically evolving networks, not just additional nodes getting connected to the present network? So what I understand by dynamically evolving network is that the strength of the edges might change, or the existence of the edges might change, correct? Is that what you mean by dynamically evolving network, Hari Shankar? If that is the case, then yes, you can. You can define a series of networks and you can give them timestamps, and then say you want to see the evolution of average path length or any other metric, then you can do that. Then you can do that calculation on the series of networks. Okay. So coming back to clique. let's look at the following network. Where you have this 5 click here, and you have 1 3 click here, and you have 1 3 click here, and you have 1 2 click here, and you have 1 3 click here. And Network X has inbuilt functions to enumerate all of these clicks. Now remember that each larger click is actually made up of smaller dimensional clicks, and this particular function outputs all possible clicks in this network. In order to find what I had outlined, which are called the maximal clicks in the network, you use this function called find click. And this is what we get, a list of all the maximal clicks. Now suppose we want to look at a slightly more complicated network, and you have lonely nodes and edges hanging about here. You can do a similar enumeration of clicks like this. And just to give an example of how detailed this package is, it also gives something called the something that we call the Q dimension of the network, or the dimension of the largest click in the network, which happens to be 5 because you have a pentagon here. And I encourage you to have a look at all of the documentation about all the other other parts of Network X. Okay, so there's another question. Oh no, somebody answered a previous question. Okay, great. So Nilima ma'am, I'm ending the tutorial session now.
Are you done?
Yeah.
Okay. So perfect timing. It's 5:30, and I think what we can do is there's a question in the window, Pankaj Goel. Maybe you can answer that, and then we'll take a couple of questions and stop because they're drilling outside. I can barely hear myself. But okay, I'll just turn it off so you can hear Malay.
Yeah, so calculating finding clicks is gets more and more difficult for larger and larger network size. But Network X uses the Braun-Kobosch algorithm, and I think an optimized version of the Braun-Kobosch algorithm to find these clicks, which uses like some sort of pivoting in the adjacency matrix while it is doing the depth first search, and that makes it slightly easier. Yeah. Are there any other questions?
I'm sure a number of people will have questions afterwards. Okay. So what you can try to do is to send us a message, maybe by the next tutorial session. Okay. So by the next tutorial session, if you send us a message, then we'll try to see which, of course, is an independent tutorial. This is a very basic tutorial, which actually is it covers the basic networks which we all work with. The other things are more advanced. But I think right now we'll close if you don't have any questions. But if you have anything additional to ask, please send us email. We'll send it to Malayaja so that she can answer. She can send you an answer. Is that okay?
Yes, ma'am. That's great.
So shall we close this session? I would like to thank you, Malayaja. That was very clear. And I think my class will be even more grateful because they are waiting for your session. So now they've got it. Let's see if they have anything to ask afterwards. And thanks again. This was a lot of trouble. And thank you for taking so much trouble.
I'm glad, ma'am. I had lots of fun going over the basics again.
Yeah. So can we close, Sayan? So I mean, the next session is at 7 o'clock, and maybe Sayan would like to make an announcement.